Reactive power is one of the most misunderstood concepts in power engineering. So in this video, I'll use a graphical approach to try to show exactly what reactive power is. So no or very few equations, just waveforms, some graphics, and we'll try to get an intuitive understanding of what reactive power actually is. Now, if we considered the problem in the time domain, we have very few fundamental things going on here. Okay, so we have instantaneous voltage, instantaneous current, and if you multiply instantaneous voltage by instantaneous current, then we have instantaneous power. And this would be exactly what would happen if we had a perfectly resistive circuit, so just a voltage source and a resistor. And the key thing to take notice of here is the fact that the instantaneous power never dips below zero. It touches zero, but it never goes below zero. If it went below zero, that would imply power flow in the other direction. But with a resistive circuit, it never goes below zero. So that's important to take note of at this point. Now, take a look at the situation where we only have an inductor in the circuit. Now, of course, if you have an inductor, the voltage and current will be 90 degrees out of phase if all you have is inductance in the circuit. And you can see something quite different happens now, okay? Because instantaneous power is instantaneous voltage times instantaneous current. Now we have that phase shift between voltage and current. We now have times where the instantaneous power is going below zero. In fact, in this extreme situation where we only have inductance in the circuit, the instantaneous power is actually below zero for half the time. Okay, and this is telling us that we have power flow for half the cycle in one direction, and then the other half of the cycle is coming back in the other direction. And that's a key thing to understand. Now, I want to make something clear at this point. These two situations represent idealized extremes. Okay, what I mean by that is you can never have a perfectly resistive circuit, and you can never have a perfectly reactive circuit that's just inductance or capacitance. Okay, all practical real systems are made up of some resistance, some capacitance, and some inductance. So these represent two idealized extremes. And you might be asking the question now, why do we bother talking about these two extremes? Well, these two extremes actually have a very fundamental relationship to the true meaning of complex power. Now, of course, a real system will be made up of some inductance, some resistance, some capacitance. It depends on whether it's an overhead line, a transformer, underground cable. But the one thing they have in common is they're made up of a mix of the main lumped element components R, L, and C. And as I said before, there's no such thing as an idealized resistive circuit that doesn't have any inductance or capacitance. And there's no such thing as a completely reactive circuit that doesn't have any resistance. So everything is a mix. And when we do have this mixed kind of situation, then the waveform kind of looks like this. Okay, so it does dip below zero, but it's not like the purely reactive case where it's spending half the time below zero and half the time above zero. So when we have the mixed case like this, complex power is an attempt to split the system into two idealized systems. One which is the real power, that's the power that looks like this, and the other one which is the reactive power, and that's the power that looks like this. The first one is caused by resistance in the circuit, and the second one is caused by reactive elements in the circuit like inductance and capacitance. So the key insight here is when we talk about reactive power, what we're talking about is the part of the circuit which is causing power to flow back and forth. And when we talk about real power, we're talking about the part of the circuit where the average is above zero for the full cycle. But the key insight here is that any mixed circuit is made up of both of these components. Now, this might seem strange because I said previously that there's no way that we can have an idealized resistive or an idealized reactive circuit. So why does this make sense? Well, it kind of does make sense because what we're doing with complex power analysis is we're splitting the system. What we're doing is pulling all of the resistive elements of the circuit into one place and all of the inductive elements in the circuit into one place, and we're treating them separately. So in a way, what we have is basically two circuits happening in parallel. They don't interfere with each other, but they're idealized. Okay, so we're making mathematically two idealized situations, one that looks like this, and the other one that looks like this. And when we do complex power analysis, what we're asking is how much of that power is like this and how much of the power is like this. But fundamentally, it comes down to how much of a phase shift you have between the voltage and the current. And you can see here, as the phase difference between the voltage and current increases, then the instantaneous power spends more time below zero. Okay, and that means we have more of the reactive type of power. Okay, but if the voltage and current are perfectly in phase, then all of the power is of the resistive type. And really, with complex power, what we do is split the system up into the idealized resistive type of power and the idealized reactive type of power. And we have a shorthand way of expressing how much of each we have. So the resistive type of power is called real power, and the reactive type of power is called reactive power. And we can call this P and Q. The combination of both of these types of power, because they both exist simultaneously on a circuit, is called complex power. And it combines as P plus JQ. And this is why the analogy between, if you look at the interaction between P and Q, it's similar to the interaction between up and sideways in Cartesian geometry. Okay, it doesn't matter how far up you go, you don't go sideways at all. Okay, so in a way, these are completely separate things. And as I said before, complex power is a way for us to split the power up into two separate things. That the phenomenon that causes these things is separate. One of them is caused by inductors and capacitors. The other one is caused by resistors. They combine as complex power, but fundamentally it all goes back to the phase shift between voltage and current and the all-important dip below zero. So that was a quick guide to reactive power. As promised, no equations. This was all graphical. It was all intuitive. If you have any questions, please let me know. I'd be happy to do follow-up videos. So if there's anything you feel that I got wrong, I'd also be interested to hear. It's a tricky topic. It's a very complicated topic. But once you get your head around it, you start to see the mathematical beauty and elegance of complex power. So thank you for watching. I'll see you in the next video.